Assalamualaikum warahmatullahi wabarakatuh, and good morning to all my students. Okay, so welcome to today's lecture on the last topic in chapter 5. Okay, multi-level shifting. So last week we have already studied basic shifting techniques such as ASK, FSK, and PSK. And we look at the general equation for these three techniques, the spectrum, bandwidth performance, bit error rate, and the plot diagrams also for these techniques. Okay, and today we'll continue with multi-level shift keying. Okay, so with multi-level shift keying, um, there's a new concept, yeah, of this multi-level that is different from what you have learned before. Okay, so for multi-level shift keying, one bit can be represented by a symbol. Okay, so we know that our carrier signal that is modulated by our digital signal can be represented, um, can be changed in terms of its amplitude, frequency, or phase. Okay, so normally, yeah, like in ASK, FSK, or PSK, we have bit 1 and bit 0, right? Okay, bit 1 or bit 0. For ASK, for instance, we can represent bit 1 with maybe 5 volt and bit 0, 0 volt. With PSK, can represent this, maybe using this one, 0 degree, and for bit 0, 180 degree. And finally for FSK, let's say this one we give one frequency, F1, FC1, this one FC2. Okay, so these are the symbols, yeah, for SK, PSK, and FSK respectively, where this represent changes in the voltage, and this is phase, and finally this one in frequency. So one symbol, yeah, these are all known as symbols. One symbol like this one, 0 voltage, represent 1 bit. One symbol of 5 volt represent, yeah, 1 bit, bit 0, and this one bit 1. So that's what is meant by one symbol represented by 1 bit. Okay, so here the number of symbols is equal to, since we use only 1 bit, so n is equal to 1. So m, the number of symbols, is equal to 2 to the power of n. So here is 2 to the power of 1, meaning 2. So here m is equal to 2, meaning we use 2 symbols, yeah, to represent two possible bits, or two total possible bits that can be represented, like this one, 0 and 1. Okay, so bit 0 and bit 1. So these two conditions need to be represented by using 2 symbols. Okay, so actually, uh, in order to make our system become more bandwidth efficient, we can represent each symbol. If each symbol can represent more than 1 bits. Okay, so this is what is meant by multi-level shift keying. Okay, a certain or a specific value of voltage, okay, can be represent, uh, for example, let's say 2.5. Okay, this can be used to represent, instead of 1 or 0, it can represent 0, 0, for example. So in this case, this one symbol of 2.5 volt, one voltage value, represent 2 bits. Okay, so by having or by using this concept, okay, uh, we can make better use of bandwidth in a system. Okay, so before we learn about bit rate, so what's new in this multi-level shifting is the term baud rate. Baud rate is equal to symbol rate. Okay, so if you use if a symbol is used to represent more than 1 bit, then baud rate will be less than bit rate. Okay, and the relationship between bit rate and baud rate is follows this equation where baud rate is equal to bit rate divided by n, where n is the number of bits, equal to log 2m. Okay, and for a certain number of n bits, m equal to 2 to the power of n symbols are required. Okay, let's look at this example. If we use 2 bits, yeah, the number of symbols that are used are 2 to the power of 2 or 4 symbols. Okay, with 2 bits, and for these 2 bits we required m equal to 2 to the power of 2 equal to 4 symbols, and these 4 symbols will represent 4 combinations based on these 2 bits, which is 00, 01, 10, and 11. Okay, so let's say we have okay, so these are bits required. Okay, so we need to define for, if for example we use multi-level ASK, yeah, we need to define 4 different voltage values. Okay, let's say this one uh, positive 5, this one positive 2.5, this one minus 2.5, less minus 5, for example. So instead of 2, there are 4 different voltage values to represent 4 different combinations based on 2 bits. Okay, so if we use more bits, then more symbols are required to represent the higher combinations of bits. Okay, if 3 bits, then the number of symbols are 2 to the power of 3 or 8 symbols. If 4 bits, then it's 2 to the power of 4 or 16 symbols. And this concept or technique is applicable to all ASK, FSK, and PSK. However, multi-level PSK has proven to be useful or more practical. Okay, so we have learned before that in terms of bandwidth performance and also noise performance, PSK has the best, right? So it uses the least bandwidth, okay, and it has the best noise performance. Okay, so when we use multi-level, okay, more symbols are required, so the system can be will be more complex, and noise performance also um, will be um, becomes, in terms of the requirements for noise, is also becoming more stringent. Okay, so that's why PSK has been proven to be more useful or practical in this case. Okay, so for the remaining explanation, especially for this course, we'll concentrate or focus on um, QPSK or 4 PSK. And this one means quadrature PSK, meaning that M is equal to 4 or 4 symbols. So for the remaining, we'll go into the detail in QPSK technique. Okay, so if you look at the current advancement that's happening, especially in the advancement of wireless network generations. Okay. So when higher generations of wireless networks were introduced, um, the speed or bit rates for these new networks will be much higher compared to the predecessor. Yeah, like 4G is higher than 3G, 5G is higher, the rate of 5G higher than 4 or 3G. So one of the important um, key technology that enables this to happen is the use of multi-level shifting techniques. So these kinds of new networks, not only four, it can be used up to 64, 128, and so on. In terms of number of symbols to represent the high number of bits. But for our class, we look at the basic, which is QPSK, and hopefully this can become a good foundation for you to understand more advanced multi-level shifting techniques in the future. Okay, so let's move to our next slide. Okay, so in QPSK, one symbol represents 2 bits. Okay, since it's PSK, phase shifting, the symbol used is phase. Yeah, so each phase is represented by 2 bits. If the BPSK, okay, BPSK before we use 0 and 180 degree. With QPSK, the 360 will be divided by 4 symbols. So the difference will be 90 degree. Yeah. So 4 different symbols will be represented by um, 4 bit combinations: 00, 01, 10, and 11. And the phase will vary from 0 to 360 degree, and the difference is 90 degree. Okay, compared to binary PSK, difference 180 degree. For QPSK, difference is 90 degree. Okay, so it changes from 45 degree to 135 to 2225 and 315 degree. Okay, and in multi-level shifting techniques, we have this term or concept known as the spectrum efficiency. Okay, so spectrum efficiency is defined as the bit rate divided by bandwidth. Yeah. So for QPSK, that uses 2 bits per symbols. Okay, so the efficiency is 2 bit per second per hertz. Okay, so this part represents the number of bits that used per symbol. Okay, so the unit is bit per second per hertz. Okay, for QPSK, since we use 2 bits, then it's 2 bit per second per hertz. Yeah, and in QPSK, the for practical use of QPSK, the technique that is used to map between bits and phase is known as the gray code. Okay, so the 45 degree is given to or mapped to bit 11, 135 degree to 01, 225, 00, and 315, 10. Okay, so if you notice, um, between the neighboring bits, the change that happens only of 1 bit. Okay, I'll show this in our next slide. Okay, So this is the equations mathematically to represent um, 1 1 0 1 0 0 and 1 0. Okay, pi over 4 45 for 1 1, and then after that 0 1 1 0 0, and then finally 1 0. Okay, so this is the general equation for this above. Yeah. So A here is the amplitude of our carrier signal, and this is 2m minus 1 pi over 4, where m uh, is integer 1, 2, 3, and 4. And for m equal to 1, it's 4 bit 1, 1, 2, 0, 1, 3, 0, 0, and 4, 1, 0. If, for example, m is equal to 1, then, okay, m equal to 1, then this part becomes 1, so it's pi over 4. Okay, 1 comes pi over 4, our phase. If m equal to 2, it's 3 pi over 4. So 3 pi, 3 pi over 4, and so on. Okay, so but in terms of the order of bit, you have to follow, starting from 1 1, 0 1, 0 0, and 1 0. If you notice, when it moves from the first to second, only one bit change. Okay, which is bit this one. Yeah, and then from here to here, it's now this one, from 1 to 0. And then after that, 0 1. Okay, so between neighboring faces, only one bit change. So this is uh, designed such a way so that the probability of error will be less. So to avoid higher probability of errors in this case. Okay, so the QPSK can be constructed using two BPSKs, BPSK in phase and quadrature. So the even bits, for example, will be assigned as in phase, the odd bits quadrature. So this is our original bit streams, from A naught, 1, 2, 3, 4, 5. So there are total 6 bits. So the bit duration in this case is TB. Okay. So when we want to implement QPSK, okay, we'll convert from this series to parallel, even and odd. So from A0, A0, A2, and A4 will be assigned to in phase, 1, 3, 5 to the quadrature Q. So you can notice the bit rate here, it's reduced by half, and the bit duration also will be longer, double. Okay, so the combination of these two BPSKs, okay, is BPSK I and Q, and can see the constellation diagram of this BPSK I and Q. So this is BPSK I. Okay, so the phase is between 0 and 180 degree. 0 and 180 degree BPSK I. And then BPSK Q, this is BPSK Q. So the difference between two faces is also 180 degree, but the reference is from 90 to 270 degree. Yeah, so this is known as the quadrature BPSK channel or channel Q, and this is channel I. Okay, so in order to produce QPSK, by combining these two BPSKs, we will add and these two. So we combine. So this is the constellation diagram of the combined BPSKI and BPSKQ. So so this is the BPSKI part, okay, from 0 to 180 degree. So it can be represented by cos omega t and minus cos omega t. Okay, and the BPSKQ, this one can be represented by sine omega t and minus sine omega t. So this is BPSKQ. This part is BPSKI. Yeah, the horizontal BPSKI. The is vertical EVP is BPSKQ. So when you combine, um, then we add these two together. So the first phase 45 degree is cos omega naught t plus sine omega naught t. Okay, so okay, we can understand this, yeah, by using vector concept. So cos and plus cos, and then plus sine, we go up, right? Plus sine, plus cos, plus sine. So this is the general equation, cos plus sine, that can also be represented in terms of phasor, cos omega naught t plus 45 degree, the angle, from reference to this line. So it's cos omega naught t plus sine omega naught t, or cos omega naught t plus 45 degree. So, and this is for bit 1, 1. Okay. And then for bit, and for the next bit, 0, 1. Okay. So difference between them is 90 degree. Yeah. So equation wise can be represented by, okay, minus cos, then plus sine. Minus cos plus sine, or cos omega naught t plus 335 degree. This will be 0, 1. And the same thing for the other faces. Yeah. So this is minus cos minus sine. Sorry. Okay. Minus cos minus sine. This one is plus cos. Yeah, plus cos minus sine. Okay. So need to understand. Start with 1, 1, 0, 1, 0, 0, and then 1, 0. So if we consider the same bit rate, yeah, if you compare um, BPSK and QPSK, so if the bit rate is similar, then the spectrum of QPSK is half of the BPSK. Okay. So this is the constellation diagram, okay, of QPSK signals. So I hope you can understand the constellation diagram and can reproduce it whenever it's necessary. Okay. So now let's look at the. Okay, I'll stop here first. Then we continue with new video on the block diagram of QPSK and a transmitter and receiver.